Okay, so we are going to discuss today about something called supremum and infimum. In a standard calculus course that you might have done in your high school, you might not have heard these words, they are not really told in your high school, but these are a very slight generalization of the idea of maximum and minimum. One might say that a real calculus course possibly does not need it, but it does need it because without these ideas it is very difficult to prove, for example, the notion of this intermediate value theorem. We will show the intermediate value theorem as an application of these ideas. Now, what do I mean by a supremum? Supremum means something super, so it is something related to the maximum, and infimum means something lower, inferior, so it is something related to the minimum. So, let us now define two things. One is an upper bound, one is called a lower bound. So, of course, you might have upper bound of what, lower bound of what. So, upper bound and lower bound are a given subset of the real line. So, S is a subset of R. Then alpha is an upper bound if alpha is greater than equal to x for all, this is a sign for all, this inverted A, for all x element of S. So, any number which is bigger than alpha is also an upper bound. So, there could be infinite such upper bounds, as you know that the real number line is uncountable. So, of course, if you want to be more precise, then you should write alpha element of the real line. So, real number is an upper bound to S if this holds. Similarly, so we take again S subset of R, then beta element of R is a lower bound if beta itself is less than equal to x for all x element of S. Now, observe one thing, that any number less than beta is also a lower bound. So, for example, if you look at this set, the open interval 0, 1. So, 2 is a upper bound, 1.5 is a upper bound. In fact, 1 is also an upper bound. In this case, for example, minus 1 is a lower bound, minus 2 is a lower bound, minus half is a lower bound, and 0 is a lower bound by this definition. But among all these upper bounds, you see 1 appears to be the one which is the least, has the least value, and among the lower bounds, 0 is the one which seems to have the greatest value. So, this looks so obvious that you really do not go and try to prove that there exists a lower bound or there exists an upper bound, least upper bound or greatest lower bound. You take them as an axiom. So, first axiom is called the least upper bound axiom or LUB axiom. A least upper bound exists. So, axiom is something which is so obvious a truth that you do not really define it. So, what is the least upper bounds? So, similarly, there is something called the greatest lower bound. So, here I call this as the 1 as the LUB and 0 as the greatest lower bound. Another more nice looking name for LUB is supremum, and a nice looking name for GLB is infimum. Now, LUB axiom says a least upper bound exists. Similarly, you have the GLB axiom, which also says a greatest lower bound exists for S, for actually for any subset of R basically. Maybe I should write for any S not equal to phi and S subset of R. Now, obviously, whenever I was discussing this upper bound and lower bound, and because I have mentioned this x element of S, I am in my hindsight actually am assuming this fact that this set must be non-empty, because otherwise you can say that okay, if you take the empty set, this is called a vacuous reasoning in mathematical logic, that because there is no element, I can say that every element in the real line is the greatest is the upper bound, every line is the lower element is the lower bound, because there is no element there. So, every number can be thought of convention, you can make a convention that every real number is bigger than any element in phi, because phi has really no number. So, then there is no upper bound supremum or infimum. So, this is what happens, and of course, I am not going to define this. This simply means that x is an LUB of S if x is an upper bound and x is less than equal to y for all y which is an upper bound, which is an upper bound for S. So, I will expect that the students can write down the definition of GLB, which will simply say that x is a lower bound and x is bigger than all the y's which are also lower bounds of S. So, because it is so obvious, we take this for granted that these exist. But what does it more mathematically mean? Structurally, what does it mean? It means the following. Suppose you have taken this line 0 and 1 and you are claiming that 1 is a supremum. So, sometimes you mention this, you write in this way, x is equal to supremum of the set S, or say z equal to the infimum of the set S. This is the standard notation that you use in mathematics. So, if you take the set 0 1, what is happening? What does this lowest upper bound means? That is, any number which is lower than that given number x, it does not mean how much lower, even if it is very slightly less, it cannot be a upper bound. Means if I decrease the value of 1, which I am claiming here is the greatest lower bound or the supremum, is the supremum of the interval 0 1. Now, if I am claiming that 1 is the least upper bound, means any number which is lower than 1 cannot be an upper bound. So, if I take any epsilon greater than 0, no matter how small, and consider one minus epsilon, then 1 is an upper bound. So, if 1 is upper bound, if I consider 1 minus epsilon, means 1 minus epsilon, then 1 minus epsilon cannot be an upper bound. It cannot be an upper bound. So, if it cannot be an upper bound, what does it mean? It means that there exists, which I write in short, that there exists x from 0 1 such that x is strictly bigger than 1 minus epsilon. So, 1 minus epsilon cannot be an upper bound and is less than equal to 1. Oh, sorry, right. So, for all x element of 0 1 such that this would happen. So, x, there has to be some x which has to be bigger than 1 minus epsilon, okay. Then only you can break the fact, then only 1 becomes the greatest lower bound or the supremum. Similarly, for 0, you see if you increase the value of 0 to 0 plus epsilon, there must be some x which is strictly lesser than 0 plus epsilon, which breaks the fact that this new number 0 plus epsilon or epsilon cannot be a lower bound. So, this can be generalized, this idea. For example, if you look at this, if you take now the closed interval 0 1, then 1 and 0 is again the supremum and infimum, but the difference between the open interval 0 1 and the closed interval 0 1 is that 1 and 0 belongs, the supremum and infimum belongs to the set, but here the supremum and infimum does not belong to the set. Right, when I am talking about maximum and minimum, essentially I am trying to talk about something which is belonging to the set. That is the idea. That is, if you go back and look into the discussion on maximum and minimum, that is what it means. That if you look at the image space of a function, then f of a b, then we are trying to find the maximum and minimum, basically a supremum and infimum which is in that set. So, there is, this is a subtle difference between infimum and minimum, supremum and maximum. So, what is the general way of writing an element alpha element of R is a supremum of S if for any epsilon greater than 0 there exists x element of S such that 0 is strict, such that alpha minus epsilon is, so you reduce the alpha, cannot be a upper bound, hence it will be strictly less than x, and this is less than equal to alpha. So, you might ask me why you have put less than here, here you have not put less than, because here what happens that no x can be equal to 1 in this set, but here in general you do not know. So, this is the general definition, because for example, if you take a set like this, and 2. So, your set is 0 1 union the singleton set 2, so disconnected set. Now, what is the supremum of this set? 2 is an upper bound, 3 is an upper bound, but 1.5 is not an upper bound here, because 2 is bigger than 1.5. But then if I decrease 2 by say a little very small amount, it becomes 2 minus epsilon. Then what is that element x which is bigger than 2 minus epsilon strictly, but less than or equal to this? In this particular case where you have these disconnected situations, then equality would come. So, in this particular case 2 minus epsilon, 2 is my chosen x. So, this is something you have to be very careful about and you have to remember that. Similarly, if you look at now infimum, so a real number beta greater than beta element of R is an infimum of S if given epsilon greater than 0 no matter how small, there exists x element of S such that beta is less than equal to x, which is strictly less than beta plus epsilon. So, again you could have a similar situation like this, where you have say the set S is 0 union 1 2. So, it is 0 and here is the closed interval 1 2. So, you know the 2 is the supremum, in this case 0 was the infimum, but you know 1 is not the infimum, 0 is the infimum, 0 is the greatest lower bound, because 1 point say half is not the lower bound, right, because 0 is less than that. So, in this sort of cases, in this particular choice, if you take say 0 plus 0 plus 0.00001 as epsilon, so you come just very near 0, some point here. Then what is the element x which will satisfy this? In this case, we have to choose x to be 0. So, these are the cases for which you have equality here, but you always have to have strict inequality here, because you have to break the fact that b plus epsilon cannot be an upper bound, cannot be a lower bound. In this case, alpha minus epsilon cannot be an upper bound. This is something which you have to keep in mind, and this is exceptionally important. So, here is this little difference between supremum and infimum. So, supremum and infimum may not be an element of the set, but maximum and minimum has to be in the element of the set. So, in this case I can say 1 is the maximum of all the values, all the numbers here in 0 1, and 0 is the least value or the minimum value. So, there is a subtle difference, but this subtle difference actually helps you, and we will now, after having a brief idea, we will now go and prove the intermediate value theorem in its simplest form using this idea of supremum and infimum. So, the proof given in Spivak. Spivak, as I told you, is a very good book on calculus written by Michael Spivak. So, here you will see we will use this idea of supremum and infimum in a very intelligent way, and this is the same idea that we had given you already in when we discussed the intermediate value theorem. I gave you the same idea. So, that same idea, that partitioning up and getting things done, that same idea is very tactfully given here, but it is very easy to remember. So, we are going to prove the IVT or the intermediate value theorem in its most basic form, intermediate value theorem. Let f, so you already know this, a b to r be a continuous function and let when the product of f a into f b should be negative, and just let us for the sake of it, and let f a is negative and f b is positive, then there exists an C strictly lying between a and b such that f c is 0. Then there exists C in the open interval a b, or even if you write in the closed interval, it does not matter, because C cannot be either A or B, such that so here is your function, or drawing always helps. So this is my A and B. It is not that I have to always draw it on the positive part, I can take any part, but okay, just for the heck of it. So this is your f of A, and this is your f of b. So, f of a is negative, f of b is positive. Now, how would I do the proof? What are the steps? In order to do the proof, first I have to observe that because since f a is strictly greater, since f is continuous and f a is strictly greater than 0, there is a neighborhood around a here I cannot have full neighborhoods, but only half neighborhoods. So, there is a neighborhood around A such that f of A would be strictly less than, f of x would be strictly less than 0. So, I can find a delta such that in between the interval A to A plus delta, there for all x, f of x would remain to be strictly less than negative. So, I so given, which means since f A is strictly negative, there exists delta greater than 0 such that for all x element of A, in fact you can say A also, does not matter, f of x is strictly negative. This, so there may be not one delta, there can be more than any deltas, because you can, as if you keep on shrinking the delta values, you will have more deltas, right. So, you can just keep on trying and see to which extent I can keep on moving, that is basically the idea. So, construct a set A. What does it contain? It contains all x in AB such that, or I should write it in a much more simpler way, it consists of all x in AB, maybe such that f of x is negative on A x. Let me construct this set. So, if I take any delta, if I take any number x which is smaller than A plus delta, then over that A x it is still negative. So, find all those x's such that f x is negative on this set. So, this is one set that we have constructed. Now, obviously x is non-empty, because f of A is negative, A to A is obviously one interval, a singleton point. The singleton point is also interval, a degenerate interval, but still an interval. So, A is not equal to phi for all x in A x. For y element of x for So, here is a little correction, sorry, so what I am trying to do is find those x's, those endpoints. So, here is one x, here all the x is negative, all the y values that you take between this interval is negative. Then you take this, the function value remains negative, then you take this, function value remains negative. Now, here I have a set which is non-empty. Now, what am I supposed to do with this? So, this is what I am going to do next. So, we will hear the idea of supremum and infimum, you will see will become really effective. Now, once we have A not equal to phi, so basically we are generating these x's here. So, we want to say that A has a supremum. How will we say that? Because you see B is an upper bound of A. B is an upper bound of A. Since f b is strictly bigger than 0, because for all values there the function value is strictly less than 0. So, f b is strictly bigger than 0. Please understand this point, that B has to be an upper bound, because B cannot be included in this set. So, here what we are doing, we are increasing these x's, the x's are gradually increasing, not decreasing. So, if you have for 1x, then obviously if you decrease the x, the function value will still remain negative on that interval. So, basically you are increasing these x's, the x values here are increasing in the interval, it is moving away from A. So, B over the whole interval a b, if you take b at the point b, if you take a b, the whole function does not remain negative because the function value a b is positive. So, b must be an upper bound, right, b has to be bigger than all those x's. So, b is an upper bound, but hence since f is continuous, in short I am writing CONT, there exists delta 1 greater than 0 such that for all x element of b minus delta 1 b, f of x must be strictly less than 0, yes, strictly greater than 0. So, this is what is happening, this is the definition, but it comes from the fact that we have already studied in the last class when we studied continuous functions. Now, what is this issue, what does this do? So, what does it tell me? So, any x here also must be an upper bound. So, we are basically telling that b is not only upper bound, there are elements which are less than b which are upper bound. So, the least upper bound must be less than b. So, hence if alpha is equal to supremum of A, then alpha is not equal to B. Now, we do not know, f of alpha could be strictly bigger than 0, f of alpha could be strictly less than 0, right. So, now we claim that f alpha is equal to 0. Actually, what would happen? Here you are increasing from x, increasing the x's till the function remains negative on that interval ax, and only at the crossing point that thing will stop. And here you are decreasing the values of x, you are decreasing the x values, you are making the interval x be bigger and bigger, but the values of x are decreasing on which the function is positive, and where the function crosses it has to hit that supremum. So, the supremum is a point where the function would actually, supremum of the set A is the point alpha where the function will actually take the value 0, alpha or c maybe. If c is equal to supremum, then we are going to prove that fc is equal to 0, okay, because we have written c here. So, let us put c equal to that. So, we claim that fc is equal to 0. So, how do you do it? So, we have to say fc strictly less than 0 and fc strictly greater than 0, these two cases are not possible, it cannot take these values. So, we have to take away these things. So, I will argue for this case. So, you can similarly argue for this case. This is for the student to argue out, the viewers, and this is for me to tell you how the argument will go. So, if c is strictly less than 0, so c is obviously bigger than a because it is supremum, and c is obviously less than b naturally. So, naturally you know that this c is essentially lying between a and b, that is obviously clear from the constructions that we have done. And so, if fc is strictly less than 0, so there exists delta dash such that for all x element of c minus delta to c plus delta, f of x, so sorry, c minus delta dash to c plus delta dash, f of x would be strictly less than 0. Now, since c is equal to supremum of a and delta dash greater than 0, there exists x naught element of A such that now you say why it is not equal to C x naught. See here the interval is continuous, it is not a this set that you will have, it will form of x's which are continuous. You will start from A and you make a very small move, the x will move continuously and you keep on forming those intervals. So here the set is A, the set A is a connected set. When here there is not one set union some other set, here it is just one full set, right, there is no gap like the ones we had discussed in the previous examples. So hence you may always, when you do not have any gaps, you can always choose in these conditions this way, but if you have a gap then there is a issue, but here you can always choose in this condition this way. So there is a x naught such that this happens, right, okay. Now of course over A x naught, over A x naught, what happens? A x naught, f is negative, A is negative over A x naught because x naught is in A, and over A x naught you know that this is negative. Now take any x1 element of C to C plus delta dash, sorry this is delta dash, C to C plus delta dash. So what would happen? F of x1 must be strictly less than 0. Now in this whole interval, because fc is strictly less than 0, in this whole interval f of function value is less than 0. So on the interval x0 to x1 f is negative, f is negative, and you know the interval a to x naught it is anyway negative. So what does it mean? It implies that f is negative on a to x1, right, on this. Hence x1 is an element of A, but x1 is strictly bigger than, but x1 is strictly bigger than C, contradicting the fact that C is the supremum, contradicting that C is equal to supremum of A. In a similar way you can argue for the other case too, that if C cannot be strictly bigger than 0, if C is strictly bigger than 0 what would happen? So you have to argue from the other side, from the B side, right. So I leave that argument to you. So we have essentially shown that these things cannot happen, and which means that Fc must be equal to 0. So using this idea of supremum and infimum, of course we have actually framed this fact, but of course I am this, the argument to reject this is much more simpler. I would ask you to think about this argument, because it is very good to think about some mathematical proof, because that will give you deeper insights and more courage to do the problems that you will get, and by doing so you will learn more about the very nature of mathematics. And so I will end this thing here, but of course in the notes that I am gradually preparing you will have the proof of this done also. I am not talking about the other theorems that I proved, that bounded maximum thing, then whether that I can use supremum and infimum. I can also use that, but there is another approach to that, using sequences, which we will speak when we learn about sequences. I put sequences at the end when it becomes much more useful. So, with this we end this, we see an application of the idea of supremum and infimum. So, there are some more things. For example, you can use this idea to prove that the set N is unbounded. The natural number set is unbounded. You can use the idea of supremum and infimum. So, that this can be your coffee time thinking. Take a cup of tea or coffee and think about it. N is unbounded. So, as a mathematician, your idea should be, as a math student, you should always use one of the major tool in the hand of the mathematician. It is called proof by contradiction. Assume that N is bounded, say bounded above, bounded below, whatever, bounded above. Bounded below, you can say there is 1. So, 1 is less than everything, there is a lower bound. It is not bounded. So, it is not bounded, it is unbounded. So, unbounded means it is one of the sides is unbounded. So, it is unbounded above maybe. There is no supremum. So, prove that, assume that there is a supremum and show some contradiction. So, that can be your coffee time job. So, with this we end the thing, and the next class we are going to talk about derivatives, not in the usual way you are taught in a high school, but in a slightly, has a slightly different flavor, the way of doing things. So, you might be wondering that I have written here 2 axioms called LUB axioms. I am just giving, this is before I finish this lecture, I just want to remind you of 2 things which I have written, the LUB axiom and the GLB axiom, where I have said that okay, for any given set, non-empty set, the least upper bound exists, or a given non-empty set, the least greatest lower bound exists. But please understand that there is a additional meaning to it. Actually, it says, to be more precise, I should say, if a given set, if S is subset of R, proper subset of R and non-empty, has an upper bound, then it has a least upper bound. If it has a lower bound, then it has a greatest lower bound. So, without having lower bound and without having upper bound, a given set cannot really have a upper bound, least upper bound and a greatest lower bound. So, the LUB axiom should be, to be more precise, I was at that time just giving a connection. So, without the notion of upper bound existing, there cannot be any notion of least upper bound. So, that you have to keep in mind. So, I am just writing it more in a more very precise way. So, if S proper subset of R and S is not equal to phi, and further if S has an upper bound per bound, then it has a least upper bound. See, the idea is that if you have a set like this, say 0 to plus infinity, and you have this one-sided sets. So, these are non-empty sets, but this does not have a upper bound. So, there is no question of a finite and real number which can act as an LUB, right. Similarly, if you take a set like minus infinity to 0, then it does not have an infimum, because there is no lower bound here, you can go as less as possible. So, only when a set has an upper bound, it has a supremum, when the set has a lower bound, it has a infimum. So, without the existence of an upper bound, a set cannot have a real number which acts as a upper bound, or in the other case, if it does not have a lower bound, there is no real number which can act as infimum. So, these are the 2 things you have to very keep in mind. So, if you might just get confused if you just read that GLB, the set has a GLB. So, it was very lightly written. The idea is that once there is an upper bound, there is a least upper bound, once there is a lower bound, there is a greatest lower bound. So, thank you. So, we will see each other in the next lecture. Thank you.